Welcome to our first video on periodic trends, where we are going to look at trends in the size of atoms and ions. So for this video, our goals are going to be to identify and explain the periodic trends in atomic radius. And second, we want to identify the patterns that we see in ionic radius. So let's start off by looking at atomic radius. Now, we imagine the atom to be a sphere, essentially. So something that's spherical in shape, you can describe how large it is by talking about its volume, or you can talk about its diameter, or you can talk about its radius. Any of those measurements would give us a description of how large the atom is. Because of the way chemists and physicists measure the size of atoms, the radius of an atom, which is from the nucleus to the outer edge of the valence electrons, is the most convenient way to talk about the size of the atom. So remember, even though we're talking about a length, the radius of an atom from the middle, the nucleus, to the valence electrons, this is a description of how large the volume of this spherical atom actually is. So when we're looking at periodic trends, we are always going to describe trends in two directions. We're going to describe the trends going across the periodic table within a family, and we're going to describe the trend within a group, moving down or up on the periodic table. So let's look at what the pattern is, and then we'll explain and look at an example of why that's the case. So if we are moving within a period, and for the sake of simplicity, we'll always talk about moving right on the periodic table to start. So moving from group 1 towards the noble gases, group 18, the atomic radius decreases. If we're moving down a group from period 1 down towards period 7, the atomic radius increases. Now let's take a look at why that's the case. As we're moving right in a period, the core charge, which is a measure of the force of attraction of the nucleus on the valence electrons, is increasing. So as we're moving to the right, the force of attraction is increasing. When we're within a period, there are always the same number of inner shells of electrons. So there's no change, I'll just put NC, no change in the force of repulsion. So if the force of attraction is increasing and there's no change in repulsion, those electrons are going to be pulled closer to the nucleus. When we're within a group, moving down a group, each period adds an energy level. So we add a complete shell of electrons. So as we move down, the force of repulsion is increasing. And for neutral atoms, the core charge within a group is always the same. So there's going to be no change in the force of attraction. So now that we've identified what the trend is, let's look at an example and see how we can figure out use these patterns in the periodic table to apply to some examples. So let's identify the element here of lithium, boron, or fluorine with the smallest radius, and then explain our reasoning for that. So let's switch over to the whiteboard here and try to answer that question. You could pause the video right now and start off by drawing modified Bohr-Rutherford diagrams for those three elements. So here are my modified Bohr-Rutherford diagrams for lithium, boron, and fluorine. Before we start into some calculations and comparisons, let's take a look at what we are actually looking for in this question, which is to find the element with the smallest atomic radius. And we're going to be comparing the forces of attraction and repulsion. So what are we looking for here with a small atomic radius? Well, for a small atomic radius, we're going to be looking for an element with a high force of attraction. That's going to pull the valence electrons closer to the nucleus. And then we're also going to be looking for a low force of repulsion. Low repulsion will allow the electrons to get closer to the nucleus. So let's start off calculating the core charge for each of these three elements. As practice, this would be a good point to pause the video and do those calculations yourself. So for lithium, 3 protons, 2 inner electrons, core charge of 1. Boron, 5 protons, 2 inner electrons, a core charge of 3. And fluorine, 9 protons, 2 inner electrons, a core charge of 7. So in terms of my forces, fluorine has the highest core charge, so it has the highest force of attraction. Next up, let's look at the force of repulsion. Force of repulsion is due to shielding, which is caused by complete inner shells of electrons. And if I look at these three elements, they are all in the second period, so they all only have one complete inner shell. So there's no difference in the force of repulsion. So no difference in the force of repulsion. Fluorine has the highest force of attraction, so we would predict that fluorine would have the smallest atomic radius. So now let's formally write out a conclusion here to our example. All three atoms have the same number of complete shells, so there was no difference in the force of repulsion due to shielding. Fluorine has the largest core charge, so has the strongest force of attraction. And therefore, since a strong force of attraction will bring the valence electrons closer to the nucleus, fluorine has the smallest radius. So I just want to highlight the points in my conclusion here. My first 2 points clearly identify the differences or the similarities in the force of repulsion and the force of attraction. Even though the force of repulsion didn't change, I want to explicitly identify that in my conclusion so that the reader knows that you understand that it does have an effect. And then finally, in my conclusion, I connect the factor that is changing the force of attraction to the question and come up with a conclusion. And I have justified these three arguments here with modified Bohr-Rutherford diagrams and core charge calculations. Now let's look at ionic radius. So ionic radius is a measure of the size of any ion. So an ion is an atom which has gained or lost an electrons. So it has a positive or negative charge. So one point of confusion is the difference between a common ion and the ability for an atom or an element to form any ion. So let's just take a look at an example here of an element such as magnesium. So if you look at your periodic table, you'll see that magnesium typically forms a 2+ ion. So we would say this is the common ion or the naturally occurring ion that magnesium forms. In a chemical reaction, magnesium often loses 2 electrons. So that is the common ion. But magnesium, if we put in the right amount of energy, we could form a magnesium 3+ ion. We could form a magnesium 6+ ion. We'll see when we talk about energy that if you just keep putting in energy, we can knock off more electrons. Likewise, we could probably put in some energy and force magnesium to form a 2 minus, force magnesium to gain electrons. So what we're going to be talking about here are the common ions, because these are the ones that most often occur, and these are going to be the ones that result in a significant change in size for each element. The common ions for the elements in the S and P block, which are the elements that are often referred to as the representative elements. So basically, not the F block and not the transition metals. The most common ions almost always result in a loss of a complete valence shell or the completion of a complete valence shell. And you've learned that in earlier grades that like our example, magnesium forms a 2 plus ion because it has 2 valence electrons, and that results in a stable complete valence shell. So for these common ions, the cations are always going to be significantly smaller than the original atom. So when an atom loses electrons, and that results in the loss of their outer shell, that will result in a much smaller atom. If an atom gains electrons and that results in a completion of their outer valence shell, that will result in a significantly larger ion than the original atom. Now that might seem obvious, but it has nothing to do with just adding electrons and the electrons taking up space. It all has to do with the forces within the atom. Specifically, changes in core charge or shielding. So let's look at an example of an element which typically forms a cation. Sodium typically forms a 1 plus ion. And before we go and look at the ion, let's calculate the core charge for the sodium atom. So sodium has 1 outer electron, 10 inner electrons, and sodium has 11 protons. So let's just write down that core charge right there. Yes, come out. Okay, starting in 3, 2. So let's look at an example of an element which typically forms a cation or a positively charged ion. Sodium in group 1 typically will form a 1 plus ion. And before we look at the ion, let's just calculate the core charge of the sodium atom. So for the atom, the core charge, sodium has 11 protons, 10 inner electrons, 2 plus 8. So it has a core charge of 1, a very weak core charge. So when sodium forms an ion, that 1 valence electron is lost. And now what used to be an inner shell of electrons is now the outer shell of electrons. So now let's calculate the new core charge for the ion. So the protons have not changed at all. We still have 11 protons. But now we only have 2 inner electrons. So the core charge now is 9. So just from losing an electron, the force of attraction experienced by the valence electrons increases significantly. A much larger force of attraction results in a much smaller ion. So those valence electrons are pulled in much closer to the nucleus. Let's now look at the formation of an anion. Chlorine has 7 valence electrons, and chlorine typically forms a 1 minus anion. So it typically will gain 1 electron. If 1 electron is added to its outer shell, we end up with a 1 minus chloride ion. But now we have an extra complete shell of electrons, that outer shell, and this increases shielding. Therefore, we're going to increase the electron repulsion. As a result, the size of the ion increases compared with the size of the original atom. So once again, with cations and anions, the size changes that we see due to the loss or completion of a valence shell has nothing to do with the electrons actually taking up physical space. It has to do with changes or significant changes in core charge and or shielding.